that how to prove something. Can you tell me how to disprove something?
By contradiction.
Yes, but is it not very much easy to disprove something as compared to prove something? You all believe this thing or not?
No.
Okay. Since this thing is very simple, you can just square a plus b, and square means not applying the formula for a square, writing two brackets and multiplying them, or using some geometric interpretation to do this. But you believe this is wrong.
Alright.
Okay. But maybe you don't know that how to prove it algebraically, how to prove it geometrically, but you know this is wrong, this is not true, and you want to disprove this thing. So you can provide only one example that shows that the left hand side is not equal to right hand side, then you are okay. We call such examples to be counterexamples. If you provide one counterexample, then you can disprove. So proving something is very much difficult, like you go a lengthy process and you apply some sort of mathematical foundations, but disproving is very easy. You want to disprove something, provide some counterexample. But if you ask me one question that whether this is well defined or not, and then I can say that this is not well defined. I must mention what do I mean by A and B. I must mention. If I'm not mentioning what is A here, what is B here, so simply you can't do anything. Since on the fundamental level we are teaching to the students, it doesn't matter because we are always dealing with the set of real numbers. But if I mention that A and B are real numbers and I want you to prove or disprove, you say, okay, this is wrong, we know very well, it means we have to disprove this thing. So you will provide only one example for which this does not hold, and that example is called counterexample. Counterexample is just one example that shows that this side is not equal to this side. You can take, let's say A is 2 and B is 3, you put here and you will get something like that. So I think for these two values this is going to be false. Okay, so to disprove something, provide one counterexample that goes against that particular thing. But if I say this thing, I say A, B and reals, but I specify that A is 0. Then you can believe that this is true. Then you can believe. You just put A is equal to 0, then 0 plus B would be B, because 0 is additive identity. Sometimes when you go for interviews, these questions are asked. In Sakurai especially, you take quadratic equation. Okay, there are no in-depth questions in quadratic equation. What they will ask you? Okay, they will ask you, okay, put here 0, 0 plus B is B, why? The thing is that identity. 0 is additive identity. So 0 plus B becomes B, and if you put 0 here, 0 square becomes 0 because 0 multiplied by 0 is defined as 0. And 0 plus B square again becomes B square. B square, you are okay. Yes, sir. So this is a tip that whenever you are going to take any fundamental topic, you should know the fundamentals. That's why we are going to do so. You are going to solve any equation which is like this. It's linear equation. So you do like this, and you do like this. But you have to like provide some mathematical insights for every step. Like you subtract 3 on both sides because the additive inverse of 3 is minus 3, and then that becomes 0. We know very well that 0 is additive identity and so on. Okay, so other thing is that I provide you with a statement, all primes are odd. Is it true or false? All primes are odd.
False.
So what do? You just provide one counter example.
Yes, sir.
Then the statement becomes disproved.
Disproved.
All primes are odd. How can we write this thing in this way? In some sort of implication. Like for all x to be in P, and it implies x belongs to set of odd numbers. It means you take any prime, it must be odd. But this statement is false.
False.
Because you can provide one counter example. You will say that let's take x is equal to 2, which is prime, but it is not odd. So this is counter example. It means your this particular statement is false and it is disproved.
Disproved.
So if we see that these are very fundamental things. Okay.
Excuse me, पंजाब टेक्स्ट जो ये अक्सर ऐसा है रियलनेस में क्वेश्चन अक्सर ही हुआ p of क्वेश्चन नंबर जो स्क्वायर को रेडी कर 2 बराबर अक्सर ही हुआ हां उसमें मैं ऐसा काउंटर एग्जांपल उनके ऐसा प्रूफ कर रहा हूं आंखें दे वो ते काउंटर एग्जांपल थी सके थो पर मानो जो उनमें ऐसा से प्रूफ कर दिखाई होंगे ता जो त जने भी को
what are lemmas, what are corollaries, what are propositions, and then we are going to discuss how to prove theorems. And this is something very much easy. There is no any in-depth mathematics in this. If we talk about definition, what is it? We are just discussing. What is the definition?
True statement. Or we are defining something. We are giving actually the definition.
Yes, yes.
We are actually naming something.
Yes, yes, that is
Labeling something.
So one thing is that we are going to name something, that's definition. The second thing is the mathematical explanation of something. That's the definition. We are talking about mathematical definitions. So we'll say that the mathematical explanation of something is called definition. But that explanation must be precise enough. It should not include each and every detail. It should include the main points. Okay, when this is there, this is called this. That's all. Then it is called definition. And the problem is sometimes you can't question a definition. Why that is so? You cannot question a definition. Okay, why this value is this and why this definition is like that. You can't say. You can ask that why this theorem holds, what is the proof of this theorem, but you can't ask that why this definition is like that. If you ask, then you have to redefine the things, then you have to create a new mathematics. This is the thing. What is a theorem?
A true statement.
A true statement, logical statement, a true statement which should be proved. And it needs a proof and it should be proved. So if we take theorem and proposition, there is slightly a slight difference between these two things. A theorem is simply a proposition and proposition is a theorem. But a proposition is of lesser importance than a theorem. Sometimes you need propositions to prove a theorem. It means you prove 2-3 propositions, then those propositions lead you to a particular theorem. So these are just mathematical statements which we need to prove. A corollary is something that we deduce from a theorem. Corollary is something that we deduce from a theorem. Any example?
Just like equilateral triangle is a triangle.
Equilateral triangle is a triangle. But we can say that I am going to provide a theorem. Is it written here? For all x and all.
X square. Yes, x square is x minus.
This is true, we know very well.
Yes,
I am going to deduce something out of this. For all x, this is true. I am going to take it down to integers. Since integers are real numbers, if something is true for all the real numbers, it must be true for all the integers. So I am going to call this particular thing a theorem, and I am going to call this particular thing a corollary. It's true. Okay. So what else do we have? What are axioms and postulates?
Condition, just like condition.
Conditions.
Requirements, things which must be satisfied. Actually, some condition which must be true. Actually,
The properties which are okay, theoretical properties and
Postulates are mainly related to geometry, mainly postulates,
Yes.
and geometry and physics. And postulates are basically the things which do not need proof. And sometimes some people call them definitions, but they are not definitions. They are the fundamental assumptions you need to prove something. And axioms are always some sort of postulates. And to build a theory, you need some axioms. Like in mathematics, mostly up to set of real numbers, we say that every number in the set of real numbers represents some sort of measurement. It means you can use any real number to measure something. Now the question is that pi is a real number, and pi shows a concrete measurement of the area of a circle with radius 1. So the fundamental axiom is all the set of real numbers is basically the numbers which are used to measure something. The measurement can be length, can be thickness, can be depth, can be area, can be volume, can be anything. So in every course of study there are some fundamental axioms that are necessary. Like in physics, the people believe that Newton's laws are valid in whole of this universe. So these are the fundamental assumptions of the subject that they are studying so far. But there are some people who are going against those axioms, and then they say that okay, the mathematics which is based on some sort of foundations
classic
is not a good mathematics. And there are some people, especially there is one Dr. N.J. Weilberger from Australia, and he has a YouTube channel, and he is against the fundamentals that we have done so far. He is against the theory of infinite semels, like we use dy by dx and dx. Dx means an infinite semel. He is against that theory. So basically he is challenging the fundamentals of mathematics. But people ask him, okay, you are going to challenge, give us an alternative, give us a better alternative. So this is going to be the main problem, that he is unable to give some sort of better alternatives to this theory. And this is very much difficult. Some theory has been built from the thousands of years. How can you provide an alternative to that? Especially mathematics has been evolving for thousands of years as compared to physics, which is not so much good background. And the modern physics is from, I think, 1900s, and the physics that we are studying in our schools is just 400s or 500 years back, but the mathematics is very old. So how can you change that particular theory? You can, but it is very much difficult. What is the proof of a theorem?
satisfactory statements which satisfy us.
Yes. So it is just an explanation of a theorem using mathematical logic and mathematical rules that simply leads the hypothesis to the conclusion. It's an explanation that leads us from hypothesis to conclusion, but it is some sort of mathematical explanation using the laws, rules, axioms and postulates which we study and which we believe in mathematics. You cannot use something which is outside mathematics. Okay, now the main thing is that how to prove theorems. So there are certain ways to prove the theorems. We are going to write every way and discuss one example of each, and then we are going to end this particular thing. And maybe we will not discuss everything because this is not concerned, but we are going to just give you a rough sketch that what you need to do in this course. Then we have some sort of number theoretic things in this course, but we will be doing those things when we are going to start number theory in detail. Then we are going to end this and we will be moving towards some other course in the next session on Sunday.
And what about conjecture?
Ji sir, I am coming to that right now. Conjecture. Are you saying conjecture?
Ji. So this whole family is discussed actually.
Yes. So, conjecture. Have you heard this thing ever before? Conjecture. So it's simply a mathematical statement that is true,
We have no.
but without any proof. You have theorems which can be proved. Like if I'm going to put forward a new theorem, I will always give you a proof, and if so many mathematicians are agree with that, they will say that okay, this is a theorem based on these fundamental assumptions. But a conjecture is something which is true, and you believe it is true, but it has no proof. Any example in the field of mathematics?
फिजिक्स में जी हमने उन दो रखता है तो ये कहने मास लाइट स्पीड से ट्रेवल करते एनर्जी में ट्रेवल की दो
It has proof.
right now
It has mathematical proof.
it has right now proof
Yes.
at that time उन्होंने हुई कौन बात थी इसकी
Yes. But Einstein gave proof, I think. First he assumed the things, then he gave proof. It is the, I think complete formula is E is equal to mc square plus, I think p square and c power 4. It is. P square is for, I think, momentum or something else.
yes. C is the speed of light.
C is the speed of light. This is a complete formula. I don't know exactly, but there is a term containing P. P is for momentum, but they consider the momentum of particles to be zero. I don't know why. There is a reason behind that. Then they only take E is equal to mc square. So it has proof, and it had proof at that time. But the problem is that it is not verifiable experimentally. You can't verify it because it is not possible for an object with some mass to travel with the speed of light. It's not possible. In these times, maybe in future.
Coming future.
Okay, there is a famous conjecture, what we call Goldbach or Goldbach, what you call it, conjecture. That is that any natural number, I think, is the sum of two primes for all n to be set of natural numbers.
Wow.
So you can take any natural number, it will always be the sum of two primes, but I think it is a statement, I don't know exactly, but can you think of any natural number which is a sum of two primes? But natural numbers greater than
2, 3, I guess.
greater than 2 or 3. Okay, let us assume this. Take any integer, 4 is equal to 2 plus 2 5, 2 plus 3, 2 plus 3, sum of two primes, 6, 3 plus 3, 7,
2 plus
5 plus 2, 8, 5 plus 3, 9, 7 plus 2, 10, 7 plus 3. So take any natural number, sum of two primes. There's no proof. But there's condition that natural number should be either greater than 2 or greater than 3. I don't know exactly. But it is that. So if you prove this thing, I think this is $1 million problem. This is. There is a Riemann hypothesis in number 3, but I think it has been solved by a British mathematician in 90s. I heard somewhere, I don't know exactly. There is like solution of Navier-Stokes equation in fluid mechanics, CFD. Okay, so methods are the ways to prove theorems. Number 1 is direct method. So I'm not writing all, we are writing one and discussing its example, then going to the next one. Direct method is a bit easy. I say let m be an integer, it means for all m in the set of integers, if m is odd, implies m cube is odd. So direct method means you will take your hypothesis or whatever given the statement is, and you have to apply some mathematical formulations on this, then it must lead to this thing. And this particular theorem can be proved with the help of direct method. You assume m is odd, and whenever this particular statement is given to you, you always assume that m can be written in this form.
2k plus 1.
Yes, let m is equal to 2k plus 1 for all k to be in the set of integers. You put any integer here, then the result will always be odd. So if you prove something related to odd, you have to write 2k plus 1 or 2r plus 1 or 2n plus 1. And if you prove something to be even, you just write 2k.
2K. Yes, sir.
And then you have to cube this thing, and it means you have to cube this thing, 2k plus 1 whole cube, and you have to deduce something like this, 2 times something plus 1. The result must be this. It means then m cube will be equal to this, and this is the form of an odd number. So you just cube this thing and simplify, take common or do some other things, and the final answer must be in this form. Then you believe that m cube is also odd. So this is the proof that how can you say that m cube will also be odd, and this particular proof is called direct proof. So I think it is doable. Just you apply the formula of cube.
Yes.
How do you prove this thing?
Completing square method.
Yes. I give you a quadratic equation, and I want you to prove this thing. What you do? You apply completing square method here.
Yes.
Okay, you give completing square method. Okay, what you do? First you
Divide A.
A,
Yes, sir.
then shift the constant to right hand side.
Yes, sir.
Then 1 upon 2 multiplied by coefficient of x whole square, added on both sides. Then making completing a square, taking a square root, and then finding the value of x is x.
Yes.
Then it will lead you to here.
Yes.
So this is direct proof, I think. In this example, we have to, we are going to use the direct proof method. But how about you are given this thing? But if you are given this double implication,
From this we can
Yes.
deduce this.
Yes, sir.
then you took this, you reached here.
Now.
That is the half of the proof. When you are given this implication, then you have to take this,
And reach to there.
and it's easy.
Hmm.
You multiply 2a this side,
Yes, sir.
you take minus b, you square both sides, plus minus is cancelled.
Yes.
You take minus 4ac and b square on this side, you are done. It's simple. But you can also do, you can take this value of x, put it here as well as here, and solve this, the result must be satisfied. This is another way. But whenever you see this sign, you always have to do two proofs. One proof is in this direction, you always write this and you prove whatever it is. Then you always write this and you prove another side. So there are two parts always. If you are doing half, it is just half proof. Okay, this is direct method. Another is proof by cases. It's a bit easy. Number 2, proof by cases. So let me take an example. And for this you can refer the book by, I think, Mathematical Thinking or How to Think Like a Mathematician by Kevin Austin. So okay. N square plus 3n plus 7 is odd for all m in Z. So you take any integer, this is something very easy. You take any integer if you put that value there, the answer will always be an odd number. You can see, put here 0, 7, put here 1, 1 plus 3, 4, 11, 2, 2 square,
4,
10, 17.
Yes, sir.
So minus 1, this is going to be 1, 7 plus 1, 8, 8 minus 3, 5. So you put any integer, the result is going to be odd number. Now how to prove? So you have to do some sort of cases like case 1, when you take this integer to be 0, and case 2, when you take integer to be even, and case 3, when you take integer to be odd. You can do in this way. And if you put 0 here, it's straightforward. N square plus 3n plus 7 becomes 7. If n is 0. And this, the result is odd number. Okay? Now you put 2k here. 2k square 3 times 2k plus 7. This becomes 4k square
Plus 6k.
6k plus 7. You can write it 4k square plus 6k plus 6 plus 1. You can take 2 common and 2k square plus 3k plus 3 plus 1. If you are able to write something in this form, it means the answer must be odd.
Yes, sir.
Because a number which is an integer multiplied by 2 is always even, and if you add 1 to an even number, the answer is always odd. Similarly, you can do this. So this is how you prove something by cases. You divide the theorem in different cases, then you prove. And this is very much common. Thing is proof by contradiction. Proof by contradiction. So, how to prove something by contradiction?
In the start we assume something is true, and in the end we...
If we take this example that square root of 2 is irrational. Now you assume something,
that it is rational,
yes,
and then in
with
the
certain
end,
conditions. You assume one thing, that square root of 2 is rational, like it is equal to p by q, but you put extra conditions that
q does not equal to
no, p by q is the simplest form. Simplest form means it is in reduced form. Reduced form means like you cannot, any number cannot divide p by q. Like this fraction should be 2 by 3 or 3 by 4. This fraction should not be 3 by 6.
Yes.
Like 3 by 6 is divisible by 3.
Yes.
You assume this thing. Then this assumption leads to something
which is
contradictory to your assumptions.
Yes, sir.
Then we believe that, okay, we are saying this is rational, but since it leads to something that is a contradiction, so it is false. If it is false, then this must be true.
Yes, sir.
This is what we call the proof by contradiction.
Contradiction.
You prove something is irrational, which is difficult. You take it rational with certain assumptions, whatever you like. But some people ask a question that why we are taking p by q to be in simplest form. We can take p by q in some other forms. Like p by q is 4 by 8, why not we are taking that? But the thing is that if you are taking 4 by 8, it is again equal to 1 by 2. So we are just assuming that whatever it is, but p and q have no common divisor except one.
Co-prime level.
Yes, co-prime. Yes,
Not
Co-prime.
further divisible actually.
yes. Co-prime means their highest common factor is one. So the same thing. So this leads to something which contradicts this. Then we can say that our assumption and this particular thing is wrong. It means that this is right. So we can prove this thing, but again it will take a lot of time. I am going to find a simple example, if possible, otherwise we are going to leave it. But proof by contradiction is this method and this works in this way. And if you study that book by Kevin Houston, it has very basic examples in which you can apply this method proof by contradiction. But if you want other basic examples, you can study the course on number theory, because the proofs in another courses would be a bit hard as compared to number theory and mathematical thinking. Like the proofs in functional or topology will be based on same idea, but they would be a bit complicated. What is another method?
Prove by supposition. Suppose. What's the name?
By induction. Induction is very
Powerful,
basic.
powerful.
Yes, it's very powerful.
Encouraged actually.
Yes, it is encouraged to be done. In most of the cases, it is being done because it is easy as compared to others. Proof by induction. And what do you mean by proof by contrapositive? We know very well that if a statement, so this is proof by contrapositive. We know very well that P implies Q is same as negation of Q implies negation of P, and this is called the contrapositive of statement. If we are able to prove this thing, it means that it is same as this, but sometimes it is not very much easy to prove this thing. So we prove this particular statement. If this is true, obviously this statement would be true. As I told you earlier, that contrapositive of a statement is equivalent to the statement itself. So any example, proof by contrapositive. So let me do it here. So let n be an integer, it means for all n to be in the set of integers. If n square is even, then it implies that n is even. If the square of a number is even, it implies that the number itself must be even. Is it true? You take any square number which is even. What are square numbers? 1, 4, 9, 16, 25, 36. Then 36 is a square of what? 36 is even, implies 6 is even. So our condition is that if n square is even, then n is even. What is the contrapositive? If n is
Even.
not even, then n square is not odd, not even. So the contrapositive is n is not even, implies n is
Square is not even.
n square is not even. Can I rephrase this? Can I say this is n is odd, implies n square is odd?
Yes.
Is it okay?
Yes.
So this is the statement, this is its contrapositive.
Yes, sir.
But this is equivalent to this.
Yes.
Now you have to prove this thing. And to prove this thing is very easy. If n is odd, n square is odd. If you prove this, it means you are done with this. This is what we call the control. Maybe to prove this is a bit difficult. Maybe. So we are going to take its contrapositive, and this contrapositive is very easy to prove. And if this is done, means this is done. This is the book by Kevin Hobson. And another thing is, the bright side of mathematics.
This is a channel actually.
Yes. It is very good about pure mathematics. He does mathematical thinking, real, functional, measure theory, and probability as well. Now he has started a series on what we call complex analysis as well. He is doing a bit rigor, but the videos are like animated and like he is not writing on board, and the length of every video is 10 to 12 minutes only, but very beautiful content. And this book is readable, everyone knows, and you can just read it within a month, or if you want within a week, but at least it is possible in a month.
How to book?
How to think like a math. Another set, you have to prove two things. One thing is that A is subset of B,
B
is subset of A. For this, what you need to do, you have to take any element from XA,
Which
and you have, it must lead to B. Then this is true. And here X belongs to B, it leads to X belongs to A, then this must be true. You can prove this thing by the same argument. A complement intersection, B complement. And sometimes in some of the courses it is given that prove that following statements are equivalent. So what do we mean by that?
A equals to B, B equals to C, so A equals to C.
Yes. So how many statements do we have here? Basically we have two statements, A and B. And what we need to do, we need to prove that A and B both are equal. It's a bit easy. If you want to prove that A implies B, what you need to do, you have to take A and you have to prove B out of that. But how many statements are there? Two statements. But if you have, the question is, prove that following statements are equivalent. And the statements are statement A, B, C, D, E. 5 statements are given to you. Then you have to prove that. The statements are, okay, V is a vector space. This is statement A. Statement B is that V must contain an identity element with respect to addition. For example, C is V must be distributed with respect to scalar multiplication or whatever. So there are some statements. You have to prove these are statements. To prove these means to prove that these are equivalent. It means that A implies B, B implies A, B implies C, C implies B, C implies D, D implies C, D implies E, E implies D, E implies A implies E, A implies C, C implies A. So this never ends. So they consider you only do this thing. A implies B, B implies C, C implies D, D implies E, E implies A.
That's it.
When you are done with this, the proof of this equivalence is done. So you have these statements in linear algebra and functional. You only do this thing. This is proof number 1, 2, 3, 4, 5 proofs. Okay, so let's end it here.